Okay, so let us continue. So we have been discussing uh, operations on processes. So the first operation was, and operations on processes usually happen through system calls. So till now we have discussed two system calls: fork, which is used for creating a process, and exec, which is meant for uh, replacing a process with some other code. As in, maybe you want the child to run some other code, say something like ls or something, or some program even which you have written, then you can call exec. Now, so we will discuss more about other system calls today, but before that, I just wanted to give you some practical application of this kind of processes. So this is why I was asking at the beginning today about what is happening in your networks lab and course. So from what I understand is that your first assignment was that you have designed a server and a client, and the client will send a file to the server, and the server will count the number of lines, words, etc., and return back to the client. Fine. But you see, so this is one kind of server and client where possibly it's expected that there will be only one client which will talk to the server. But you see, there can be different types of applications. Often there are servers which are expected to talk to many clients at a time. Think about an email server. Right? So many clients log into that server at a one point of time. So, like, suppose a particular server is running. Let's say that is the process. So you have written the code, the server is running. Now, so I guess since you have done this assignment, you have the concept of listening at a socket. Do you? Okay.
Yes, sir.
Okay, fine. Okay, so maybe yeah, that is what I am trying to say. Maybe in your second assignment, what you will do, let's see. So you have already have the concept of listening at a socket. So suppose this server is listening at a socket. Now a client logs in. So now immediately the server has to do two things together. One is service this client. Maybe that client will ask for some service, like say a service like what you have designed, sending a file and then the server gets, I mean, computes the number of lines, etc. But also the server has to go on listening for other clients, because the server that I am talking about, it is not meant for just talking to one client. It is meant to be a server like an email server where many clients can log in and get some service. So now how can the server do to both things? One is servicing this client which has logged in, another is going on listening for other clients. So the thing is the two things cannot be done simultaneously. So one like practical design policy is that the server forks the child. The child services this client which has logged in, and the parent goes on listening for other requests. Suppose another client logs in. So the parent will again fork another child. So every time a client logs in, the parent forks a child. That child goes on talking to the client which has logged in, and the server goes on listening at the port, at the socket. Okay, that is a practical application. Now think about it. Suppose the server has, forked a child to talk to the client. Now, how to talk to that client? You can write your own code, just like in this slide you see. You can, inside the child process, you can define how the um, client should talk to the, how the child should talk to the client. Like say, okay, let us take that assignment that, okay, the client sends a file, and the child, you can write in this child process function the code to open the file and write the, I mean, count the number of lines, etc., etc. The other thing is maybe you want to do something complicated for which there is already a program, let's say. So maybe you have written it or some other program. So the other way is you exec the child. So the child execs some other code. Okay. So again, which to choose, that is your decision. Both are fine. Both are technically correct. inside this program also you can write what the child is supposed to do. Maybe that is what you have done in your first assignment. But also another design can be that if child executes some other code. Okay. Now, that is just, I mean, again, just to make the idea clear, this is not the only option. So suppose you have really a client, a server where many clients log in. So suppose 100 clients have logged in. That's okay. The server may fork 100 children. But again, it might seem that, okay, forking 100 processes will make the system very slow, because every process, every child process should be given some memory. Then lots of bookkeeping activities will go on. There has to be context switches among 100 processes. So all these things build up. Like I mean, if you go on forking processes, there is a cost that you have to pay. So someone might also design the server in another way, that okay, the server will just fork 5 children. Okay. And these children will handle all the clients. So even if the 100 clients have logged in, these 5 children processes somehow will handle all the clients. They will multiplex, as in all the clients are waiting. Maybe the clients will wait, fine. But the server won't get too overcrowded, as in server only has 5 processes, or even 6 processes, the parent and 5 children. So that way the clients may have to wait a bit, because 5 children are talking to 100 clients. So there will be some kind of multiplexing going on. The clients will find it things a bit slow maybe, but the server will be in a more healthier state because not many processes are there. So again, which design to choose, that is your business, your decision. If you expect too many clients to log into your server, maybe you won't go for forking a child for every client. But if it is a very critical mission where you don't expect too many clients to log in, but then all clients should be given very fast service, then you will possibly create a child for every client. So these things are your decisions. Like similarly, like whether you exec a different program or you write in this code itself, that is again your decision. So don't think that which is correct, which is wrong. Both are correct. Depending on the application, you take these decisions. The OS gives you these mechanisms. How to use those mechanisms, that is your decision. Like, so these mechanisms are kind of tools in a toolbox. How to use those tools, that the kernel won't tell you. That is up to you. Okay, so let me go on. So we were discussing the third system call, which is wait. So like in this example, which I was telling, maybe a server forking a client. Maybe the server has no business waiting for the child. Maybe. So in the first example that I said, maybe yeah. So maybe the server just forks one client for every. Sorry, the server just forks one child for every client, and then the server does not care what that child does. The child will service the client. So here the server may not wait. But then think of the second example that I said. The server creates exactly 5 clients, and all these clients just service all these children, the 5 children of the server process services the clients. Then the server might actually want to wait for some of the clients. Or okay, no, this is a bad example. No, it will not, because the server has to go on listening at the socket. No, so okay, I'm saying that maybe for some other application, it may be that the server would not like to do anything until the client exits. Okay, so this example, forget this example. This is not a case where the server will wait for the client, because the server will have to go on listening at the socket. But for some other example application, it might be that the server has nothing to do until the client terminates. So there, this wait system call can be used. The parent can call wait to tell the kernel that it does not want to run unless or until the client terminates. So that if the parent calls wait, then the parent execution is suspended, and it will. So basically, you remember there is a waiting state. So possibly the server process will, or the parent process will enter that waiting state, and it will again be ready only after the child terminates. However, we discussed in detail yesterday that you cannot guarantee that whether the parent will run first or the child will run first. So it might happen that after the child was created, the child ran quickly and the child had a very small work to do. So it just quickly finished. Later, when the CPU was scheduled to the parent called wait. But then by then the child has already terminated. Then the wait call will return immediately and the parent will proceed as in, yeah. But if the parent calls wait and the child has not terminated yet, then the parent will be blocked or it will be in the waiting state until the child terminates. Now there are two variants of the wait call. One is simple wait. If the parent calls wait, that means it will suspend execution of the current process until one of its children terminates. As I said, a parent can create multiple children. So if just the parent calls wait, then the execution of the parent will be suspended until any one of its children terminates. Okay. Otherwise, let's say the parent can also tell the kernel that it is waiting for a particular child. So maybe out of the 5 children that it has created, it is waiting for a particular child to terminate. Then also there is this mechanism of wait PID. Here actually it takes as argument a PID. So this is the PID of the child. So this is the way of telling the parent telling the kernel that I am waiting for this particular child with this PID. Okay. And remember, the parent knows the ID of every child. That is what was returned by the fork system call. Okay. So this is about wait. Now, what about process termination? So a child process, how can it terminate, or any process for that matter? So one way is it executes the last statement. Like say, yeah, the exit, you might also, I mean, maybe the last statement in main, which is say, maybe you return 0. Okay. So another way is there, which you might know, exit call. So also from exit, if you call exit, if a process called exit, usually there is a argument to exit. So what is this return 0 or exit? So this is a way of returning status data to the parent via wait. So if any parent is waiting for the termination of this process, then this return value, which is say return 0 as the last statement of main, or exit 0 or exit 1, this value will be returned back to that parent. Okay. So often this is the mechanism because maybe the parent wants to know some value from the child, or more commonly, the parent at least wants to know that the child finished its work properly. So the convention is if everything went according to expectation, return 0. And non-zero values can be returned to indicate some error condition. That is the convention. I mean, it's up to you, but the convention is if everything went properly, return 0. Otherwise, return some positive value, which might actually, give you some idea about what error occurred. So just a quick, so now one reason why, let's say, the parent can wait for a child is exactly this, what's written in the last line. So maybe the parent, let's say you can decide on an application where the parent has maybe dynamically allocated a large array, right? And let's think of this application that, I mean, it's not a very practical one, but let's say that a huge array needs to be, processed in some way. So maybe there are 1 million elements. Each element needs to be processed in some way independently. So if you run a loop for 1 million iterations, it will take a lot of time. So one way is the parent dynamically allocates the array, etc., etc., and then it creates 10 children. Each of those children work on 1/10 of the array. Okay. So suppose this is the situation. So then you have two considerations. One is this parent, after it has created the 10 children, should possibly wait for those children, because the parent does not have anything extra to do other than doing that operation on that array, which is being done by the children. So possibly the parent will wait. The other thing is, after all those children have terminated, the parent has to do possibly some cleanup operation. Like it should, free that dynamically allocated array. Right? So for those kind of things, the parent sometimes waits for the child, and after all the children terminates, it will deallocate the resources and so on. Also, another point to note here is that suppose a child terminates. This deallocation of resources may be done by the parent, but also there is someone else who might need to deallocate some resources. Can you think who? Any answers? Oh, people are awake. Okay. Okay. So basically what I was trying to tell is the kernel will also need to deallocate some resources possibly. Because remember that when this process, yeah, okay. Yes, what Ravi said, that is the idea. So the kernel has, every time a process starts, the kernel needs to allocate some resources for it. Right? So there will be a PCB entry created, then some amount of memory will be allocated to the process. So maybe when a process ends, the kernel may have to also reallocate some resources which was allocated to this process earlier. Okay. Okay. Oh, okay. Here is some small code snippet to demonstrate this exit call. So you see the child process here. Let's talk about the parent first. So the parent possibly forked this child process. That part is not shown here, but let's say it was forked and so on. At some point, the parent can call this. So PID equal to wait and %status. Okay. So this wait system call, this has to inform the parent of two things. One is which child terminated. So that is typically returned by wait. Okay, so PID equal to wait, you see, wait will return the process ID of that child which terminated. Also, there is this mechanism that the child can send back one status code to the parent. Like you see exit 2. So this 2 possibly means something that the child and the parent understands. So 2 is not a random number. 2 means something. That will be available to the parent in this variable status. Okay. That value which has been with which the child exited, that will be available to the parent in this variable status. Using this, the parent might know a few things, as in, did the child could the child do its work properly, or did some error condition occur, or something like that. Okay. By the way, have you in your daily life, have you seen such error codes? In your daily life, while using some computer system, etc., have you seen such error codes which tries to tell you what went wrong? Yeah, exactly. So Guru Prasad, good answer. HTTP errors, like, yeah, Nisarg also, good. So when you are browsing the internet, often something goes wrong. You will be given some kind of you'll be shown some kind of a code like 403, 402. So those numbers actually have meanings. You can look up what does error 403 mean. Okay. Okay. Aryan is telling while installation. Possibly. Yes. That also, then also maybe some error codes can be shown, which will tell you so something particular went wrong. Okay. So yeah, so that those kinds of error codes are meant by what is being shown here. The child can exit with some code, which maybe usually the convention is to return 0 if everything went well. But if not, if some error occurred, then you can return a non-zero value, and the parent can actually get that value to understand what went wrong. Okay. So we discussed 3 calls or 4 calls. Let us see a complete example with all those. So you see, they have to include some header files in order to make these system calls. And then let's say, so you have PID underscore T, PID. The parent forks a child. Okay, then it checks. If PID equal to 0, then it's an error condition. So maybe it prints out in the standard error, fork failed, and return 1. Okay. Else if PID equal to 0, see, this is the child process. So this part is the child process, PID equal to 0. So here it says exec LP bin ls null. So again, as I said, you should look up the system calls to understand what are the arguments which exec LP takes. So exec LP is one variant of exec. But intuitively you can understand this is trying to run the ls command. Okay. So slash bin slash ls. What is slash bin slash ls? What is that? Yes, what Ashutosh is telling. So basically that is the executable actually. So that is the ls command. So when even in the shell, well, shell prompt, when you write ls, actually this is the program which is running. So yeah, this is the absolute path. Right? So when we say ls, actually that is the program that is running. So that is what is being exec here. Right? So the child process will be completely replaced. So instead of this code, so again understand, when the child was created, it also ran this code, which you see, because the code will be the same as the parent. But then due to this exec call, the code of ls will be replaced. I mean, the code, this code in the child will be replaced by the code of ls. Okay. And else, this is the parent process. The parent is waiting for the child to complete, so it calls await. And then see the printf child complete. Specifically understand that control will go to this printf statement, child complete, only when control returns from wait, and that will only happen after the child has completed. Okay, so this printf child complete will actually be printed once, I mean, control will reach this printf once after the child terminates. Okay, so this is a kind of small code which shows all the system calls that we have discussed till now. Now, see, this is the typical flow that, let's say, the parent will fork a child, and the child will do something, the parent will wait for it, etc., etc. But sometimes there can be exceptions. So in some operating systems, let's say, okay, so the understand that the parent terminating and the child terminating The parent and child are two different processes, right? So the parent terminating and the child terminating may be correlated or maybe not. Let's see the different cases. In some operating systems, there is a rule that all children must terminate when a process terminates. Okay, so this is called cascading termination. All children, grandchildren, etc. must be terminated when a process terminates. And OS takes care of this cascade. However, this is not the case in Linux, so we are not discussing this case in detail. Also, see this exit and wait, there can be multiple combinations. Think about it that suppose the parent forked the child and then it terminated, the parent itself terminated. Okay, so maybe now the situation is the parent is no longer active, the parent is not running anymore, it has terminated, but the child is running. So then now there are two cases, whether the parent called wait or not. So okay, okay. So one situation, one possibility is that the child terminated. That when the child terminates, kernel sees that no parent is waiting. Okay. Then the child becomes what is called a zombie process. Essentially, the child has exited, the child has completed, but no parent is waiting. So then the kernel does not have, say the child has terminated with some error code or something like that. But since no parent is waiting, the kernel does not right now know to whom to return this error code, etc. Right? So then, since the child has terminated, the kernel can deallocate most of the resources that was allocated to the child, but it cannot deallocate everything. Because who knows, maybe at some point later, the parent will call a wait, and then that error code has to be returned to, the return code with which the child terminated has to be returned to that parent. So this means that the child has terminated, but still the kernel cannot completely do away with all the bookkeeping data that it had about the child. So that kind of a situation, this child process is called, it has become a zombie process. Okay. So I think the word zombie, like from like horror stories and all, that is, we know what zombie is. So what is a zombie in like horror story literature or something like that? Okay, half dead humans. Half dead humans. Okay. Half dead humans can even be that someone is really badly injured, he's half dead. But it's not in that sense. I think zombies are more like they actually have died. Yeah, exactly. So, yeah, what Ashutosh said, they have actually died, but they still like live on for some purpose. Okay. So zombie in horror stories means that people who have actually died, but they still are around for some purpose. So the analogy is the same here. This child has actually terminated, but still there has to be the kernel has to keep some entry of that child, just because we have the parent has to, the parent may have to be returned that error code later. Okay. So yeah, so that is the analogy why these are called zombie processes. Yes. Okay. Yeah, good that Moina did not say the world needs more zombies, but yeah, as long as it is zombie movies, I guess it's okay. Now, the less sinister thing is orphan. So orphans are less sinister than zombies. Orphan is kind of more simpler to understand also. So the parent has terminated, but it did not invoke wait. Okay. So now the child is running, the child is still alive, the child is running, but the parent has terminated. So this kind of a process will be called an orphan. So actually, in some OS, this kind of process is not allowed. This is what is written in the first part of the slide. So the moment the parent terminates, all the children has to be terminated. In some OS, that is the rule. But Linux does not follow that rule. It says that if the parent has terminated, then the child will still be allowed to run, and that will be called an orphan process. Okay. So understand the difference between the zombie and the orphan. In the zombie, the child has terminated, but it still cannot be completely removed from the system, so it's zombie. And in case of an orphan process, the child is very much running, but the parent has terminated without invoking wait. So then the child becomes an orphan process. Yeah, okay. So this is okay. This slide explains zombie process. Yes, a process that has terminated, but whose parent has not yet called wait. So all processes move to this state, the zombie state, when they terminate, and remain there until the parent calls wait. And so as I said, the kernel cannot remove all the entries of this process. So there's this entry in the process table that has to be still maintained, because at some later point of time, the parent can still call wait. And then the kernel cannot tell, oh, that process terminated, therefore I have removed all entries. That the kernel won't like to tell. So it just keeps some entries in the process table so that the error code at least can be returned to the parent if it calls wait. Okay, so that is the zombie. And yeah, the orphan process is the parent terminated without invoking wait. So as I said, in some operating systems, immediately the child will be terminated also. But in Linux or Unix, that is not the policy followed. The policy followed is this: if the parent has terminated without invoking wait, this child will be made, this child will still be allowed to continue, and the init process will be assigned as its parent. Remember, we discussed this init process briefly. This is the first process created when a system boots up, and that is the only process which we said that process is the only process which is not created by a fork. Okay? So that is the first process which is created when a system starts up. So that process will be made the parent of this child in case its original parent has terminated. Okay? And the init periodically invokes wait. Okay. Okay, so this is the usual workflow between parent and child. Take this with a pinch of salt. This is usual workflow. It does not always have to be like this. So let's say there is a fork. So after that, there are two processes, parent and child. And fork returns PID equal to 0 to child and PID greater than 0 to parent. Usual workflow is the child will, run exec, and at some point it will terminate. Usually the parent will wait for it. When the child exits, the return code will be handed back to the parent, and then the parent will resume. But this is the usual workflow. There can be many variations depending on your application. The child may or may not use exec. Parent may or may not wait for the child, and so on. Okay, so any questions at this point? After this, we will start a kind of new subtopic related to processes. Any question at this point?
I actually have a question to the class. So I guess that you guys understood zombie process and orphan processes. So what is the problem if those orphan processes are not owned by init? So in the previous slide, we talked about OS actually, init process owns them and periodically invokes wait and so on. Why do OS need to do that? What is the problem otherwise for orphan processes? Mm-hmm. Ashutosh is almost correct without return to parent. Ashutosh is actually the answer that I was looking for. However, what is kernel space essentially?
So maybe Ashutosh can unmute and say.
Yeah, that will be better. So
Yes,
Ashutosh, can you yeah, go ahead, please.
yes, yes, I meant to say, I mean, all the PCBs for the process that we have, they will still stay in the kernel space, right? Even after, I mean, even after that process has died.
Uh-huh. Yeah,
Yeah,
you're correct.
that's right.
You're correct. Just with a pinch of salt, though, most of the things in the PCB will be freed because now the process is not running. It is not really taking any resources. However, the entry will remain. That means the pointer will remain, and that pointer will take up space. Each pointer 4 bytes. So if there are sufficient number of zombie processes not cleaned up, so at some point kernel will run out of the number of processes it can spawn. So even though the PCB is mostly freed, some part of it will remain, and the kernel needs to take care of it. Like these PCBs are assigned, and that will take up memory, so it will go away. Like it will mean the kernel, the assigned memory to kernel will go away at some point. That's why it calls wait. And then Rajat actually told orphan process will always be in zombie state. Um, well, that is not quite true, right? Because when you have a orphan process, that actually means a process parent terminated without invoking wait. So semantically, yes, but syntactically, like from the code point of view, these two are different things.
Actually, sir, I wrote that as an answer to your question. Like if
Okay. Yeah. Okay. Yeah, explain, Rajat. Go ahead, please.
no, sir, no, just exactly what Ashutosh said. Like it'll hog kernel memory because it won't uh, it won't have a parent, so there won't be a parent to have like to wait on it, and it won't ever come out of the zombie state. So the kernel will have to remember that there was such a process existing before.
Meaning that it needs to keep a pointer
Keep a
to the
pointer.
PCB. Yeah.
Yes.
Okay, go
Thank you,
ahead.
sir.
Thank you. Yes, SG, over to you.
Yeah, so thanks, Meena, for the discussion and others. So one thing comes out of this discussion, I hope everyone appreciates that. The designers of the kernel or the OS, like, okay, you might think that, oh, who cares about 4 bytes of space? But that's not how the designers think, right? So the understand that the OS, it's a very important part. We are having a full course on it. But after all, you would not like the OS itself to take a lot of memory or resources in your computer. Because after all, the resources are for your use, as in the system and the processes that you want to run, your applications. So if the OS starts taking lots of memory, etc., that's not an ideal place to be. So the designers of the kernel or the OS understands this, and therefore they try to keep the system as efficient and as less resource hogging as possible. Right. So the OS kind of understands that it is not the most important thing in the platform system. Actually, the resources are meant for use of other programs. And that is why we worry about reducing context switch time, uh, reducing, say, or grouping outputs together and sending them together so that I mean, too many times the context switch does not happen. So those kind of, and even like what Somaynak was especially pointed out, that we do not want too many processes just to be accumulated. Because after all, the bookkeeping entries that the kernel is storing, that's kind of overhead. So yeah, I mean, the designers of the kernel need to take these things into account. And also understand that operating systems are not only meant for huge computers with lots of memory. When your smartphones have operating systems. So in those cases, memory is more of a constraint, right? So actually, you need lightweight kernels which will take care of these things. Okay, so let's move on. So next we will start this subtopic on processes, which is inter-process communication. So I think from the idea, from the name itself, you understand when two processes communicate. So processes executing concurrently may be independent or cooperating. So till now, what we have considered are all independent processes. But sometimes processes can cooperate. For example, they can affect or be affected by other processes. They can share data, let's say for speed up in computation. This is the example I was giving a few minutes back. Maybe you have a huge array in which you have to do some operations. So you can actually create 5 processes which will share that array, and they will do some operations on that array. And design, and of course, like for modular design, sometimes you need these cooperating processes because you would not like the same process to do everything. You would like the design to be modular, let's say. So for all these different purposes, processes can need to communicate with each other. And for that, the kernel or the OS provides several mechanisms by which processes can communicate with each other. These are called IPC, inter-process communication supports. Okay. So that is what we will discuss going forward. So there are different types of IPCs which we will discuss, like shared memory, message passing through a named pipe, etc. Also, the fourth one is special, that is over a network. So you see the first three things written here, that is will be discussed in this course. And the fourth one, that is being discussed in your networks course. So understand the difference. In this course, we are talking about that multiple processes are communicating, but they are in the same system. So therefore, they can share memory. Right? So they are in the same system. On the other hand, in your networks course, what you are being taught is two processes communicating with each other, but they are in two different systems. And they're connected by a network. Right? So that is also a type of IPC. But the difference is that in that case, the two processes communicating are in two different systems. Whereas we in this course, OS course, we will focus on processes in the same system communicating with each other. So let us see the first type of IPC mechanism called shared memory. So typically this idea is this. So let's say some process creates a memory which is a special memory called shared memory. And these two processes A and B both can access this shared memory. So this shared memory is actually a part of the physical memory, which has been designated as something special that has to be shared by, that can be shared by two processes. Remember that in general what we talked is that process A will be allocated some memory and process B will be allocated some memory. A will not be allowed to access memory of B and vice versa. B will not be allowed to access memory of A. But this is a special memory, shared memory, which we will discuss the details, but we create that memory such that it will be possible for multiple processes to access that memory. Okay, so again, in these discussions, we will show some code snippets and explain the basic idea. But again, we expect you to go through, understand the details from some resources like some man pages or internet or something. Okay. So let's check some function calls. So first of all, you have this char pointer my seg. Okay. So this is, and you have a key. Okay. You have a key like some unique ID 235, let's say, in this example. This is the call shm get, which creates a shared memory segment. Shm get. So this takes as argument this key, and this let me explain this. IPC underscore create pipe 0666. First of all, okay, what is this 250? I have forgotten myself. Why not? Do you remember? Okay, this at least I have forgotten. So maybe look this up. Let us focus on this part. First of all, what is 0666? Any idea? Also, that 0 has a meaning. I mean, we could have just written 666, but that's not what we are writing. We are writing 0666. So what is this? Okay, Deep, good answer. First of all, that 0 tells you this is an octal number. Remember octal number system, base 8. And so there are 3 types of permissions associated with a file or a memory: read, write, execute. Okay, so this 6 here, this means that what this defining what kind of permissions are associated with this memory. Okay, so these are called access permissions. Yeah, these are called access permissions. So this defines whether this memory is writable or only read-only or something like that. So remember, when you open file in C, like fopen or something, then you pass on some flags saying read mode or write mode or read-only mode. It's kind of like that. When you are creating this memory, you are specifying what should be the access permissions of this memory. And IPC create is the flag which says that you want to create this new memory, right? And this pipe, what is this pipe? What is this symbol? Again, this has nothing to do with OS. This is like C programming knowledge. What is this pipe? Bitwise OR, yes. Bitwise OR. Okay, so this is how you create the shared memory segment and you define what permissions that shared memory segment will have, etc. Next, this call shm at. This is shm attach. You attach the memory segment to the address space of this process. Okay, and which memory segment? You see, this shm id is what shm get returns to you. So now that this memory, this shared memory has an ID. So that ID, by that ID, you are indicating your which shared memory to attach to this address space of this process. SHM get and SHM at, SHM attach. Okay. So
Right.
then
And
you can.
yeah, go ahead, please, and then I'll just tell what 250 means.
Okay, fine. The size maybe I forgot. Maybe. Yeah. Okay. So yeah, Maina, go on. Tell it.
Yes, pretty much size. So
Yeah.
essentially, SHM get, I mean, when you are creating a shared memory, all you are doing something like malloc, however, with more flair, and for doing so that that memory can be accessed by multiple processes. So you need to tell how much memory do you need. So 250 just tells that.
Yeah. Yeah, I just remembered that there is a simple explanation for that 250. Yeah. Okay. So that is the size. Yes. So then you have created the shared memory and then you have attached it to the address space of this process. Then you use it just like you would use any other memory. You can use this. Finally, when you are done using that memory, you detach that memory from your process address space. So detach the memory segment from the process address space. And finally, SHMCTL is another system call which marks a segment to be destroyed. Right? Actually, SHMCTL can be used for many other purposes. It is used for shared memory control, CTL control. Okay. One way of controlling is marking that it can be destroyed later. How are we saying that we are marking it for destruction? By this flag, IPC RMID. There are other purposes of SHMCTL also, which I would suggest you to look up. So typically this is the workflow. Like you create a shared memory, you attach it to your address space, process address space, use it, then you detach and you mark it later for destruction. So understand that it's pretty much the flow where how you use dynamically allocated memory. You malloc, then you use it, later you free it. So kind of lot many more system calls, etc. But basically the workflow is the same. Okay, so next we will start on some examples of this. How can shared memory systems be used? So let us discuss that next week. Okay, so we'll stop here today. Any questions? Okay, thanks everyone. We'll meet next week.
Sir,
Yes.
I had a query regarding the assignment deadline. So can it be for the lab? Can it be extended by 1 day?
Okay, 1 day. My God, I see. Seems, yeah.
Okay, so the thing is that if many people actually feel like that, then just initiate a discussion in lab discussions, and we can discuss then and there. Like it won't be for one person, but if the class feels, then our job is to make sure that you learn and you do it properly.
So even I feel that our team requires a little bit of extension. It would be very
Interesting.
So
Anyone who feels that deadline should not be extended? These
that's
are
the
two
thing.
cases,
That,
yeah.
no, that's the thing, right? So let's actually just write it, and then whoever thinks the deadline should be extended for how long, just write something, Satvik, or whoever feels like that, and then let people like in that to give a vote, and then we will take a decision. Okay? Because here, if you say yes, I don't really know who is telling and so on. So let's just make sure that that happens over lab discussions, and we will just resolve it there. No worries about it. Okay, Satvik?
So should I write it in the same chat or in the teams? Like maybe all of the students in the class can react on the message so that you can get a number.
Get a feel for what the class wants. Sure, let's do that.
Okay, Ravi has a very good question. I mean, that is something which I was expecting. So, okay, but since, I mean, I guess some people might have left. But okay, so let's see, understand the question. Like if you remember what was shown in the slide, so there used to be a key, an SHM ID, right? So suppose Ravi is asking that if a particular shared memory has been created with the key 235, that was the example. How would multiple processors know that this is the key? Because they have not spoken till now, right? So that's a very good question, actually. So actually, remember, these are cooperating processors. So that means, yeah, they have to have some cooperation before. So most possibly both of them know the key. Okay. So yeah, I mean, unless they are completely independent processes written by two different people who know nothing about each other, then they cannot use this kind of a mechanism. Okay, so they need to, I mean, that is why they are called cooperating processes. They need to have some common knowledge. Okay, fine. Okay, so yeah, I think so. Yeah. Okay then. So let's end this class. We will continue tomorrow, and we have taken note of the request about the deadline. So Mainak and I will discuss and we'll get back. Okay.
Yep.
Fine then. Thanks everyone.
Thank you guys. Bye-bye.
Bye.